or which is also known as the distributed parameter system. So far what we have discussed, right, as far as the single degree of freedom system or multi degree of freedom system. In the context of multi degree of freedom system, we have talked about 2 degree of freedom system also. So this is a special case of multi degree of freedom system, right? So those are all discrete parameter system, right? You see, all are the stiffness, damping, and masses are you can identify. Okay, there it is a mass. You can see there here it is the stiffness component, right? So that you can identify, right? Very easily you can identify that it is available there. Okay, but in continuous system, so you will not be able to separate it like that. Oh, mass is here, my spring is here, like that. Okay, and in most of the real systems are a continuous system. Okay. Okay, so for our convenience, what we do, we have discretized them, idealized them, and to make it a lumped parameter model or the discrete model, so that it is easy to handle. Okay, as we will see in the due course, that for the continuous system it will be a partial differential equation as opposed to the ordinary differential equation that is solved for the uh, discrete system or distributed parameter system, right? There it was m d2x by dt2 like that plus c into dx dt. So here it will be uh, I mean the del the partial operator will be there, because here the displacement function, okay, that is let's say u or v. For the beam it is the transverse displacement, right? That is the bending deformation. V is a function of space as well as the time t. So there will be in the equation of motion, or the governing equation of motion involves the partial differential equation. Okay, and the analytical solution or closed form solution for that only exists for a very simple system. Okay, very simple system, uniform system without much complication. Okay, or
So,
not. Yes,
so like your screen is not visible.
I have just shared it, although I have not written anything. I'm just talking now. And now it is visible, right?
Ah, yes, sir. No, it's visible.
Yeah. So just this, I mean, I am in the first slide only. Okay. So I'm just telling something regarding the continuous system. Okay. So that we will see. And where I am, so I am telling that for continuous system, the closed form solution or the exact solution basically is only available for few simple type of model or for the system. Okay, like just for an example, we'll study beam, right? We'll see that the closed form solution, or even you can find out the that natural frequency, right? Because our aim is to first find out the natural frequencies, mode shapes, and then the response. That is our target that we are doing so far for single degree, multi degree, all those things. Okay, so you will see that the closed form solution or exact determination of the frequency mode shape is possible only for a beam of uniform, I mean, cross-sectional area, everything, it is not changing, right? EI, that is flexural rigidity, is constant throughout the length of the wave, or in those cases. If it is varying along the length of the wave, cross-section is not, I mean, the uniform, that means it is not a uniform beam, then you cannot get it. Okay? So in those cases, we have to go for the approximate solution, like as I a little bit mentioned, like Rayleigh's method, or there are several other methods is there. So those are some approximate methods, and the best way is to the finite element method. Okay, so which is beyond the scope of this subject. So we'll just study the simple beam vibration problem here, and that also for we'll derive it for general type of beam. I mean, it can be varying EI and varying cross-sectional area, but finally we'll consider a uniform beam and then find out the natural frequency mode shapes, and then we'll see how to determine the, I mean, first I will validate the orthogonality of the mode shapes. Again, the orthogonality of the mode shapes is varied here, because you see the system, whether it is continuous or discrete, it is our modeling approach, right? But the system behavior is not going to change. Okay, right? And obviously, if you discretize a continuous system to a multiple degree freedom system, our response should be such that it must match with the, I mean, the exact method or the continuous system model. Okay, right? So let us move on. So as I already mentioned, in discrete system, mass damping and elasticity, that means the springs were assumed to be present only at certain discrete point in the system, right? In many cases, we need to consider the continuous distribution of mass damping elasticity and assume that each of the infinite number of points on the system, let's say cantilever, right? Distributed parameter, and there is infinite number of points which are going to vibrate, right? So there is an infinite number of degrees of freedom in a continuous system, right? So these are called continuous or distributed parameter system. Okay. So discrete system, finite degrees of freedom, defined by ordinary differential equation. Okay. And the continuous system, it is the, so it is nothing but an initial value problem, right? Because we specify the initial displacement and velocity. Remember, x at time t equal to 0 and x naught at time t equal to 0, right? Distributed system or continuous system, it has infinite number of degrees of freedom, partial differential equation, it's a boundary initial value problem. So here we have to incorporate initial condition as well as the boundary condition. And in fact, the eigenvalue problem is depends on the boundary condition, right? That is the natural frequency and mode shapes will be governed by the what boundary condition it has. Like for cantilever beam, it will be different from the simply supported beam. Okay, we'll see in the due course. So in general, a discrete system and the continuous system represent two distinct mathematical models. So these are just two distinct mathematical models of identical physical system. They display similar dynamical behavior, similar, not same, right? Regardless of which mathematical model is ultimately chosen, we should expect similar vibrational characteristics. That is expected. Okay. So now we will, as I already mentioned, so this continuous system, study of continuous system is a huge, huge, right? Okay. So some books are there just for the continuous system only. Okay, dynamics of a continuous system or vibration of a continuous system. Just a single book is devoted to that. Okay. So in our elementary level, we'll just study only the beam problem, and that is also Euler boundary beam, simple thin beam theory, right? That you already know. That's called thin beam theory. Okay. It is not applicable for the thick beam or deep beam, where you cannot ignore the shear deformation. Okay. So just one more thing I want to say that so basically the vibration problems of a continuous system you will find in the books the like for axial vibration of a bar, right? Vibration of a bar or a rod undergoing axial vibration. Number two, you will find out torsional vibration of a shaft. Then you can find out that beam vibration, right? Beam transverse vibration of a beam transverse vibration, right? And here in this case there could be many, right? The beam could be rotating, the beam is rotating, the beam could have axial force, the presence of axial force. Okay. Okay, and then there is Euler boundary beam and the motion could be many category could be there in this aspect. Okay, which is very important. Okay, but that we are not going to discuss. Okay, there can be, I forget one thing that here you can write is the vibration of transverse vibration of strings, transverse vibration of string or cable. Okay, string or cable, right? And you know all the strings, right, in the musical instrument. Okay, so you get different tones by actually modifying the frequency and the mode shape. Okay, that is what it is. Okay, so there can be many. So this is 1, this is 2, 3, 4, then 5 is the plate vibration, plate bending vibration, and other cell, everything is there. So we are just considering only the beam transverse vibration problem. Okay, and that is also Euler boundary beam, not subjected to any axial force or the beam is not rotating, the simple type of beam. Okay, fine. So with this background, now we will move to the, so what is our first thing? We have to formulate the equation of motion. Okay, formulate the equation of motion. So derivation of the equation of motion, right, for the beam. So let us say this is my beam. I am showing uniform, it may not be. Let's forget about it. Let me just, this is just a beam. This is my x direction, this is my y direction, and this is, let's say, z direction. It is subjected to some distributed loading. Okay, of fxt. This is x direction. So now x I will use as a coordinate system, right? And I will call this transverse displacement as v, which is a function of x and t. Okay, v is the transverse displacement of the transverse displacement of beam due to bending actually, right? Got it? And let's say the L is the length of the beam. Okay. Okay. And what approach we are going to use? We are going to use the Newton's law. Okay, Newton's law, that is the equilibrium approach by drawing a free body diagram of an elementary portion. Okay, with small element, not elementary, element portion I'll consider here. Let's say this is at some distance x. I'll consider an element of length dx. Small element I'll take out and I'll consider the equilibrium of that element and write the two equilibriums, that is the force equilibrium and another is the moment equilibrium. Okay, and then I will find out the equation of motion. Okay, please remember that for your information. Okay, or you can read it by yourself, or okay, that the same differential equation that we are going to obtain using the Newton's law can be developed using the what Hamilton's principle. Very interesting. The Hamilton principle that I talked about, right? The integration T1 of T to 2. If you remember, then what I talked, del of T minus V, I think, into plus del of WNC non-conservative forces dt is equals to, I think, something like that I have written. Right? T is the kinetic energy, P is the potential energy, and del WNC is the work done by the non-conservative forces, like the external forces or the damping forces, okay, which is non-conservative in nature. So if you do this operation also, okay, by finding out the kinetic energy, potential energy, and work done by the non-conservative forces, you have to substitute here, you have to do the integration by parts, and if you follow the procedure of the Hamilton principle, you will get the same, exactly same equation of motion, and more importantly, we will get the associated boundary conditions also. All combination of boundary condition also you can get. Okay, that is the beauty of that method. But we will not pursue that method here. Okay, we will simply use the Newton's law. That is the equilibrium approach by drawing the free body diagram of a small element here. Okay. So basically the major assumptions, the two major assumptions of the Euler boundary beam theory is applicable here, that related to statics, right? So that is what are the two assumptions? One thing is that the deformation that we are considering is very small, small deformation theory, right? Small displacement or small deformation theory. And the second thing is that it is a thin beam theory, right? There is a slender very. The beam is very long as opposed to the other two dimension. So therefore, we can ignore the shear deformation. Okay, shear deformation can be ignored. Okay, that means, in other words, a plane section which is plane and normal to the neutral surface or the reference axis will remain plane and normal to the neutral surface after the bending. Okay. So that is one assumption, and the small deformation theory. You have also remember, I think, right, that the small deformation theory. You are not considering the large deformation. If you consider large deformation, then there will be non-linearity come into the picture. Okay, so that we are not considering here. Small deformation theory. Okay. Okay. That means like higher order terms like dx square, right? Those terms which can be ignored also, and I mean the ds, right? That's the arc length, curved length. The ds is approximated as the dx. Okay. So these are related to the static assumptions. And another assumption to the dynamic, related to dynamics, is the we are ignoring the rotatory inertia. Okay. The inertia, the inertia effect, which is only due to the transverse displacement, is considered, and we are ignoring the rotatory inertia. I'll talk about that. Okay. So rotatory inertia we are ignoring because we are assuming that the slope, okay, the change of slope is very small. Okay, since the deformation is very small, the slope is very small, and you can ignore the inertia effect. It is the acceleration due to the change in slope with time. So that we are actually ignoring. Okay. So that is the part of the Timoshenko beam theory, where you consider both shear deformation and the rotary inertia. Okay. Understood? So in these assumptions, now just consider a small elementary portion of the beam of length dx. Okay. So this you have already learned, right? I think V is the shear force. This is V plus dV, the positive sign convention. Okay. This is the moment. In statics also you do like this, right? M plus dm. Okay. And here is the distributed load, arbitrary type, f of x comma t. Correct? Okay. Dx is there. Any other force is there? No, right? Okay. So these are the forces acting on the element. So just what we will do, and so what is that? Let's say it's the beam has a mass per unit length mx. Mx is the mass per unit length. That is rho into a basically, right? Unit length. Mass per unit length, and EIX, that can be varying. I mean, it can be tapered beam. EIX is the flexural rigidity. Rigidity of the beam. Okay. Now, so Newton's law, equilibrium approach, right? So first is the force equation. Force equation is the summation of forces in the upward direction, right? So upward direction I have defined as y. Y, let's say upward is positive y, that equals to, so this elemental, let's say this mass of this small element is delta m, and acceleration in the y direction, right? Force equal to mass into acceleration in this direction. This is the force equation. Correct? Okay. So now if I substitute, so please write it here, and can you tell me the expressions? Okay. Just sum up the forces and tell me what you are getting. So my transverse displacement is Vx, for your information, as a small v. Vxt is equals to the transverse beam displacement, right? Transverse displacement. So what are the forces acting in the upward direction? Positive V minus V plus dV. Then what are the forces? Fxt, right? That is f of xt into dx. Any other force? Any other force?
No, sir.
No, sir. No. That equal to delta. Inertia. Huh? What? Sum of the forces, Newton's law. We are applying Newton's law, not D'Alembert's law. We are applying Newton's law. Force equals to mass into acceleration in that direction. So force is the summation of forces is equal to mass. So mass of this elemental length will be what? M into x is the mass per unit length into dx, right? Into acceleration. What is acceleration? Del to v by del t. I am not writing here vxt. It is understood that v is a function of x. Okay? Clear? Let me write at one place maybe. Any doubt with this equation? I mean, it is not, we have not finalized it, just expression. Clear? Just written the force expression. Okay. So now the Vv got cancelled out. Now dV. So dV can be written as minus del V by del x into dx, right? Plus f of xt dx mx mass per unit dx del 2v by del t. Okay? Okay. So eliminating dx on all both sides, what I will get? I'll get minus del v by del x plus f of xt equals to mx del 2v by del t. Keep this as equation number 1. Okay. We have not formulated yet the equation of motion. So this is first equation we got from the force. Okay. Agree with this equation? Any issue? What I am writing is very bad, del 2 del v, right? This is the confusion actually. Let me modify it to this v may be shear force. I'll call S. Is it okay if I call it S for the time being? Otherwise the v may get confused. Okay. S plus. Doesn't matter. I mean, it is a convenience. ds. Let me write it here. So here everything will be again. What is there? So S minus S plus ds, because I am using small v, right, for the transverse displacement. So maybe while writing manually, so I can make, I mean, this can be confusing, right? What is small v and what is capital V. So S is the shear force. Okay, and v is my transverse displacement. So this will lead to S. Okay, now this is v minus, this is the transverse displacement. Clear? Now I will use the moment equilibrium. Okay. So moment equilibrium is that it's a summation of moment about any point. Let's say clockwise positive, you can take anti-clockwise positive, it doesn't matter. It has to be actually I naught mass moment of inertia into alpha, that is the angular acceleration. Alpha is the angular acceleration. Okay, alpha is the angular acceleration, and I naught is the mass moment of inertia. That's moment equilibrium, right? Moment of inertia, like the force equilibrium. Delta m an element mass, acceleration in the vertical direction, okay, transverse. This is this is for the force equilibrium. For moment, it will be summation of moment will be I naught into alpha. Okay. But as I already mentioned, the slope is very small. Okay, right? So we will ignore the inertia, rotary inertia effect. So this term is neglected in the Euler-Bernoulli beam hypothesis. But in Timoshenko beam theory, we'll consider this along with the shear deformation, right? So that means in Timoshenko case, your slope, right, that theta, which we Euler-Bernoulli beam we consider as a dv by dx, right? That will not be the case. With some plus, then some gamma will come into there, right? That gamma is the shear strain that you have to add. Okay. So that this is called the rotary inertia effect or rotatory inertia. Some book it is rotary inertia, some book is called the rotatory. Let us write rotatory inertia. Okay. So this effect is neglected in Euler-Bernoulli beam theorem. I should at the beginning, very beginning, I should write this is the Euler-Bernoulli. Okay. Euler-Bernoulli beam theory or thin beam theory, also known as the thin beam theory. And all deformations are small. Okay, small deformation theory. Okay, now tell me, so this equals to 0. So now what is the moment equilibrium? Please tell me, referring to the figure. Please note down the figure again, this figure, and tell me what is the, now it is your static basically, right? Moment equilibrium. Let us take moment about this point doesn't matter. Let us take about this point O, moment about all the forces about this point, and tell me what you are getting. For your convenience, I am drawing the figure again here. Okay, m plus dm s plus ds, this distance is dx, the force, arbitrary force acting in the upward direction is fxt, and we are taking moment about this point. Okay, tell me by taking moment about the point O what I am getting. Okay, so that will equate to 0, right? Because I am neglecting the rotatory inertia or rotary inertia effect. Okay. So then tell me, what should I write here? If you have any difficulty in understanding the equations or the figures, please let me know. Okay, because we are just going to presenting the Euler-Bernoulli beam theory. Then we will discuss about the free vibration problem, determination of natural frequency mode shape, orthogonality of the mode shape, and how to find out the response. That's all, and I will finish it. And I'm trying to finish it in the maximum 6 classes. Okay, so please concentrate. Okay, and let me know if you have any issue or any doubt. Okay. So please tell me what is the moment.
S dx
S dx
plus fxt dx by 2
fxt dx by 2
plus m
plus m
minus m plus dm.
minus m plus dm equals to 0, right?
Yes, sir.
M s into dx fxt into dx, right? The force, total force is dx into dx by 2, right? fxt is the distributed load.
Yes, sir. Yes.
So there should be dx into dx by 2. Dx into dx by 2, correct?
Yes, sir.
Okay. So here it will get cancelled out. Okay. So you can ignore this, right? Dx square, higher order term, small deformation theory. So what I'll get actually basically minus dm. Minus dm is again del m by del x into dx. Okay. Plus s dx equals to 0. So that means s equals to del m by del x. That you already know, right? Shear force equal to, the rate of change of this bending moment. Okay. S equals to del m by del x. Got it? That is our basic simple static equation, right? Okay. Now substituting 2 in equation number 1. Okay. This is equation 1 here. So I'll substitute here s equals to del m by del x. Okay. So what I'll get? Minus del 2 m by del x2, right? Okay. Then I can this transfer to that side. So So that how I will get it. This means, so I'll basically get, so just del s by del x, right? S equals to del m by del x. Del 2 m by del x2. So del 2 m by del x2 plus on the right hand side it is mass per unit length into del 2 v by del t2 is equals to fx. Is it okay? Anybody has doubt with this equation? Any issue with this equation? It's 2, right? Is it 2? Okay. So I have substituted equation 2 which I obtained from the moment equation neglecting the rotary inertia effect. I have got this. This is already known to you, right? That is shear force equals to del m by del x. Okay, right? Okay. And now here it is. You have learned dm by dx because there is time is not coming into the picture. Here it is everything in terms of space and time. Okay. So that's why it is. Then I have substituted that expression in the this equation number 1. S equals to dm by dx and taken to the right hand side. So I have written del 2 m by del x2 plus mx del 2 v by del t2 del 2 v by del t2 equals to fxt. Okay, clear? Okay. Now from elementary beam theory, what you know, m equals to what? M equals to, come on, what is m? How would the m is related to the curvature basically, or the differentiation of v? Okay, how it is related? M equals to
EI p square over dx square.
so EI del 2 Vy, here it is del 2 Vy del x2. That you already know, right? Okay, very simple. You can refer any mechanics material books, you will find out. Okay, for the sake of completeness, I'll quickly show it here. Okay, it's very simple. Okay, so again, go back to that beam problem. So let's say this is my beam. I'm just showing uniform one. So I'm a cross section at a distance x. So this is x direction. So I'll just quickly show it because you already know it. Okay, this is the cross section. Okay, so this will be y direction and this will be z direction. Okay, and this is my strain distribution diagram, which is linear. Strain is varying linearly. Okay, so I'm considering an elemental portion of area dA at a distance y from the neutral axis. Okay, so what is this angle? This is the slope basically, right? So order boundary beam theory, it will be, so I'm just writing in d. This is actually dl will be, if you consider, so dv by dx. Okay, that is the slope. So then at this level, what is this value? That is the displacement, right? Okay, so what is the displacement? That is the normal deformation, right? Normal deformation. Normal deformation. Normal deformation will be y into this slope, right? Y del you can write, or d you can write, whatever. I'm just showing the beam theory. So y dv by dx. So this is the this one. That is the axial deformation or the normal deformation y del v by dx. So what is strain? Epsilon is equals to derivative of the deformation, right? That is the y d2 v by dx. Correct? That is epsilon is equals to like del u by del x, right? We write that. So the displacement. So if this is your u is equals to, let's say this. Okay, u at that for this fiber, that fiber I am considering at a distance y from the neutral axis. Okay, so that is nothing but y this height multiplied by this angle, considering more small deformation. So that is y into dv by dx is the u. Okay, normal displacement. Okay, so then the normal strain, this is epsilon xx actually, xx or x whatever you write. So that is del u by del x. That is y del 2v by del x2. Correct? Using Hooke's law. Normal stress will be E into epsilon xx. That is E y del 2v by del x. Again, I am just confusing. Just write del 2 by del 2. Okay. Let's time dependency. Okay. Del 2v by del x2. Okay. Clear? Hooke's law. Linear elastic material. E into epsilon xx. That is E into y into this. Epsilon is a strain is first derivative of the displacement. Displacement is nothing but y into del v by del x. What is y? Y is just I have taken any arbitrary fiber at a distance y from the nucleus surface of elemental area dA. Okay, so this is my slope, right? Del v by del x. Right? If v is the transverse deformation. Okay, so v is the transverse deformation in the y direction. So del v by del x is the slope multiplied by y will give you this normal deformation, that is u. Del u by del x strain, normal strain. This is normal strain. This is the normal stress. Okay, so that is E into y del to v by del x. Okay, so then what is the force acting on this element? Okay, so let's say this Fe element is equals to sigma xx into cross sectional area d. Very simple, right? So E y dA del to v by del x. Correct? Again I am repeating. So this is the slope. Here the normal deformation is y, because at a distance y del v by del x. Considering small deform, no small angle, no small slope. Epsilon xx strain, first derivative of e. So y del to v by del x. Normal stress E into epsilon xx. Hooke's law apply. Ey into this. What is the force acting on that fiber? Sigma xx into d. Stress into cross sectional area d. E into y into dA by del to v by del x. Oh, we have almost done. Insert new equation in this. So what you have got? So Fe, that is for that small strip, the force acting is the E y dA del to v by del x, right? Okay. So now, what is the moment of the force about the neutral axis? Okay. What is the moment of this force Fe about the neutral axis? Yes.
dy square dA whole square with
F into y, right? Correct? Correct or not? F into y.
Yes, sir.
Yes. So the moment for that small strip F into y, that is equals to E y squared dA into del 2 by del x. So that is for small element. So for all such element, total moment is equal to integral of E outside, or you can write E outside. Y squared dA into del 2 by del x. Y squared dA integral is nothing but I. Second area moment of inertia about the neutral axis. I. Del 2 by del x. Done? Okay. So have you learned in this way or some different method? Yes. No reply. So this way you have learned, or in some different way you have learned? But you have learned, right? Huh?
So like this only.
That's this one, correct. So it's straightforward, right? That you already know. I just for the sake of completeness, I have obtained this. Now you substitute m here. So then you'll get del 2 by del x ei. So I'll write ei x. I mean that is a function of x. It can vary with along the length of the beam. Then del 2 v by del x2 plus mx del 2 v by del t2 is equals to fx. So this is our governing differential equation for transverse vibration of Euler-Bernoulli beam. Okay, that is what you have. So that is the equation of motion. Okay, right? So del 2 by del x2. So please remember this lesson and just look at that expression. If your time dependency is not there, this term will not be there, right? Then it is that all that you have learned. Okay, that distributed loading is equals to, remember EI, if it is a uniform beam, EI del 4 V by del x. Okay, so if the beam is uniform, then it will be, if the beam is uniform, then I can write EI del 4 V by del x4 plus m will also be constant, mass per unit length, everything is uniform, del 2 V by del d2 fx. Okay. So now, so you see here the differentiation with respect to time is also there as well as space is also there. Okay. And our primary variable is the V, that is the beam transverse deformation. Okay. So obviously my free vibration problem will be what? This will be 0, right? No external force. EI del 4V del x4 m del 2V by del 2 equal to. So you have to analyze this equation to find out the natural frequency and motion. Okay, because we do the free vibration analysis, right? Mx double dot undamped free vibration, mx double dot plus kx equals to 0, and then you substitute the assumed solution and obtain the eigenvalue problem and solve the ensuing equation to find out the eigenvalues, and then you find the eigenvector, right? That is done for the multi-degree freedom system. So similar type of approach will adopt here to find out the natural frequency and the motion. Okay. Now also to solve this, right? So as you can see, so in your second order differential equation that you have talked about in the context of multiple degree freedom system, so let me write here the equation again: del 4v by del x4 plus m del 2v by del t2 equal to 0. Free vibration problem, right? So as in your second order differential equation, that is the ordinary differential equation. So how many initial conditions we have used to solve the problem? How many initial condition is required?
Two, sir.
Why 2?
Initial is
Second order instant time.
Second order differential, because in the derivative over the time, time is the second order. So we have used the initial conditions ICS at the x at 0 remote. So here it will be V at x but time t equal to 0 is equal to some V naught, and V dot at some time t equal to 0 as V naught, right? So here are the two initial conditions. Now, but since it is a special dependent, so it must have some boundary conditions, because it is an initial boundary value problem, I, V, V, P. Okay, not the initial value. How many boundary conditions should be required? How many boundary conditions?
So displacement at end should be 0.
How many? I didn't ask what is displacement for. I asked you how many. Just tell me number.
Four.
One,
two, sir. Two.
4.
again tell me.
Two,
4.
sir.
4.
I can have 2, 4 like
So
that.
1.
Why two initial condition is required? Please explain again.
So
Sir,
1.
like the slope and the displacement at the fixed end should be 0.
Is the problem. I'm not asking slope, anything I'm not asking. I'm just asking how many, just a number. Okay. Here you
Sir,
told
4, sir, because it's a fourth order equation in X.
absolutely
So it will be 4.
4 boundary condition is required because it's a fourth order in space. Okay. Second order in time, 2 initial condition, fourth order, 4 boundary condition is required. Now this boundary condition is obviously going to vary depending on the physical situation. Okay. Fine. So now let us consider some typical boundary condition that you encounter. Okay. If you have used Hamilton principle, you could have seen that you have obtained the same differential equation, but along with all the combinations of the boundary condition also you will give. That is the beauty of the method. But here you are not getting. We'll just explicitly talk about that. There comes the initial condition is done, right? 2 initial condition is done. Now 4 boundary conditions. So what are those 4? We'll just talk about support by support, right? Okay. So at each support is basically the 2 boundary condition, because the beam has a 2 support condition. Okay. So if your boundary let's say boundary is fixed boundary, okay, fixed, or it's also called the clamped boundary condition. Quickly tell me what will be the boundary condition. What will be the 2 boundary condition for the fixed end?
So slope and the displacement should be 0.
That means V equal to 0 and del V by del X equals to 0. Correct?
Yes, sir.
If your boundary is pinned or simply supported also called, then
V will be 0, but dou V by dou x will be 0.
V will be 0 and
Dou V by dou x won't be 0.
yeah, that is the EI del to V by del x to will be 0. Correct? Moment is 0. Number 3,
Yes.
let's free end. Free end, what will happen?
So V not equal to 0, EI dou square V by dou x square equal to 0.
What will 0?
Moment, sir. EI dou square V by dou x square.
Moment will 0 and free end, right? Nothing is there.
Sir, V not equal to 0, sir.
V naught. What is V naught? Bending moment will be 0 and the shear force will be 0. Okay. That is del x of EI del to V by del x to will be 0. Okay. Similarly, some other boundary condition can be there. If let's say there is a mass at the free end, right, attached to the free end, so then your shear force will be equal to that mass itself, right? Like that way. Okay, or if you provide additional moment or those things, so that is the different thing. Okay, time varying moment or those things. So those are your boundary conditions. Okay, so these are typical boundary conditions. Just for your information, so this type of boundary condition, these categories, these I'm just boxing it. These, and these. Okay, this is one category, and I'm circling it. These or this category. These are the same type. So this square type you will learn later if you pursue structural analysis in a later stage, and maybe in matrix structural analysis, but in the finite element method definitely. If you do your masters, then you will definitely come across this thing, this terminology. So just I will tell about that. So if this type of boundary condition, that is for the beam, the boundary condition given on displacement and slope, these boundary conditions are called as the geometric boundary condition, directly coming out from the geometry of the system, also known as essential boundary condition. Why it is? No, not it. No, I do not need to know at this moment. Okay. Also known as the kinematic boundary condition. Kinematic boundary condition. Okay. Also known as, name of the scientist, Dirichlet boundary condition. Okay. The circle one, that means these type of things, right? This is known as the force boundary condition or natural boundary condition, or after name of the scientist, Newman boundary condition. Just remember few terminology like this type of called the geometric or essential boundary condition. You can remember these are called the force or the natural boundary condition. Okay, this circle is not called force boundary condition. Okay, there is this one, this type of, I'm just circling out, and the square one I just presented here is the geometric or essential boundary condition or Dirichlet boundary condition. So let us show here some different types of, if this type of boundary condition can be there, which is not common, although end connected to a spring damper and mass, restoring damping inertia force is balanced by the shear force, right? Okay. So one boundary condition, bending will be 0 and the shear force will be just that this one, balanced by this due to this mass function, this thing, right? Or A is the -1 minus plus, that is just okay. Now so we will now start with this equation, right? That is the free vibration equation. Okay. So for uniform beam, to m del 2 v by del t2 is equals to. So here you see v is a function of x and t. So we will assume our solution like that, which is also called the variable separation technique. Let's say v, capital V, space dependent, and capital T, time dependent. It's called variable technique of variable separation. Variable separation. Substitute there. Okay, then what you are getting? Yes. It's called technique of variable separation. Maybe I have to stop at now. I thought that I'll continue till 11:20, but it will be too much in one day, right? Okay, just tell me what expression you are getting.
EI into T into dv power 4 by dx power 4.
EI into TT into
dv power 4 by dx power 4.
now it will be D, right? Correct? Not the del.
Yes, sir.
That's
Yes, sir.
D4 Vy dx4. Then
Plus
m
m
into
into
Ex into
Ex.
T
M into what?
m into Vx into d square T by dt square.
D2 dt by d2 square equal to 0, right?
Yes, sir.
Okay. Then I will actually this I will keep it here, and then T I will put it here, and then we will solve the ensuing eigenvalue problem. The eigenvalue here, there will come the one time dependency part will come into the picture, and one space dependent. We'll discuss about that. Then we solve this problem, apply the boundary condition depending on the problem. So there can be problem like cantilever beam, right? One end fixed, other end free. Then simply supported beam. Then what other kind? Okay. Then free beam also you can consider. Free beam. Okay. So those different boundary condition can come into the picture, and you have to apply those boundary condition in the eigenvalue problem, and you have to solve the ensuing characteristic equation. Okay. Understood? What is the time? 10:56. Let me just continue a little bit. Okay, now, so you got this right? I hope this is correct. So then you just separate the what should I say, time dependent part and the space dependent part, and write the equation in that format. Something equal to something. Here you write space dependent, here you write time dependent. You are finding some resemblance with the multi-degree, right? So that is there. Okay. So this is called the variable separation technique. I am saying that my solution Vt is space dependent Vx and the time dependent Tt. Okay. So then after substituting, someone told this. Now I am asking you to write one side the derivative with respect to x and another side with respect to time and equate it. Okay. And that has to be equal to 0 because they are independently, right? Independently has to be equal to 0. Okay. Oh, sorry, some constant, not 0. Some constant. Has to be some constant. Because they are independent to each other. Yeah, so can you tell me what is the expression? From here I can see, right, 1 by t, this will be I can write, and then here I will write I by m, okay, and vx, 1 by vx, right, del 2 by del v4 is equals to, yeah, tell me please.
So EI by V
EI
by V.
and M is also there, right? This M will come down.
No, sir, actually put the M, that's it. Like, it's like N by T over there.
EI by M.
So EI by MV.
Okay, MV.
D power 4 by dx power 4.
Yes.
Equal to minus 1 by T d square T by dt square.
Okay, space dependent, time dependent. Okay. So they will be equal, obviously, since to some constant. Okay. Then we will solve this and these and separately and find out the. So this equals to some constant, this equals to some constant. Okay. That will be EI by MVX V4 Vy dx4. Okay, is equal to some constant, and then this equals to some constant. Okay. This one part and this equals to this one part. Okay, so we'll solve this problem and this will lead to our eigenvalue problem also. Okay, we'll discuss this thing in tomorrow. Fourth order equation will impose boundary condition depending on the problem that we are considering, like cantilever beam or simply supported beam, or if it is a free beam. Okay. In the solution of this differential equation, fourth order equation. Okay. So any doubt with the today's discussion so far? Okay, we'll talk about this maybe next class. So tomorrow, is there any classes there tomorrow? Tomorrow is holiday, right?
Yes, sir. Tomorrow's holiday, sir.
Oh, one more classes will be missed. Okay, so day after tomorrow at 12:30 we'll start with this eigenvalue problem. Okay, we'll again start from here maybe. Okay, for your convenience, we'll start from the basic equation. Okay, that the free vibration problem. Okay, where I have written this one. So I will get the variable separation technique I will use, and then I will separate it out. And since there one part is the time dependent, one part is the space dependent, so they can only be equal if they are equal to some constant. Okay. So then I will equate it to that to the constant, and I will get two separate equation, one time related, one space related. The space related will give me the eigenvalue problem. Okay. I will use the boundary condition appropriate to get the frequency equation or the characteristic equation. Solving that, I will get the frequency and the mode shapes. Okay. Here it is the eigenvalues and eigenfunction, not the eigenvectors here, because it is a function of x. And then the time dependent part is already known to us. That will give you the harmonic solution. Okay. Synchronous motion, time dependency is harmonic. Okay. So I'll stop it. Any doubt with today's discussion so far? So what is the mid-shame timeline as per institute rules? What is the, I mean, not mid-shame actually. I mean, what is, some time is given, right, for 2-3 days in the month, beginning of the month of November most probably, right? So during that period, I will conduct the mid-shame of 30 mark. 40 mark evaluation is already done. Okay. 30 I will conduct, then 70 will be done, and 30 will be for the end shame. Okay. That will be, I think, in the December most probably. So in the November, I don't know exact time. So you can CR, you can check it. Okay. Which
Sir,
start
12 to 16, sir.
12 to 16
Yes, sir.
November, right?
Yes, sir.
So in between that, I'll conduct the mid-sem of 30 mark, duration of 2 hours. Okay. And you please let me know the suitable date and time. Okay. Although time is there, a lot of time is there. Today is only 18th October. Okay. So between 12 to 16 only, I'll conduct the mid-sem. And then end sem as per the institute timeline. Okay. Okay, so what we have discussed today is the formulation of the equation of motion of a Euler boundary beam undergoing transverse vibration. Okay, and then we talk about different boundary conditions and how to solve that boundary initial value problem. So the technique of variable separation, we just started it. Okay, and I have given some idea. Then we will proceed ahead from this, And for at least for two examples, like for cantilever beam and simply supported beam, we'll try to find out what is the natural frequencies and the mode shapes. Okay, and we'll plot those mode shapes, what could be those, and then we'll discuss about the orthogonalities of the mode shapes. Here also it is applicable. Okay, and then we'll discuss about the modal analysis or mode superposition method by virtue of the orthogonality principle. Okay, and by using that, how to find out the response of the system. That's all we'll discuss. And maybe the Rayleigh expression in this case also I can just present, and then I will finish. Okay, thank you all. If you have doubt, you can ask me. I will be here more for 5 minutes. Otherwise, you can leave.